Welcome to this video. Today, we will be solving problem number 1994, the number of good subsets. This is a fascinating problem that challenges our understanding of subsets, prime factorization, and efficient computation. Let's dive in and explore how to approach this problem step by step. In this problem, we are given an integer array called nums, and our goal is to count how many subsets of nums qualify as good. A subset is considered good if the product of all its elements is a positive integer that can be represented as a product of one or more distinct prime numbers. This means that every element in the subset must be greater than 1, and the product of the subset's elements should only involve distinct prime factors without repetition. For example, a subset containing 2, 3 is good because both numbers are prime and their product, 6, is divisible only by the distinct primes 2 and 3. However, a subset like 4, 4 would not be good because the product, 16, involves the same prime factor, 2, multiple times. Finally, we need to return the total number of good subsets, but since the result can be very large, we must return it modulo 10 to the power of 9 plus 7. It's also important to note that subsets are defined as any collection of elements from nums, in the same order, where some elements can be excluded. Additionally, two subsets are considered different if they are derived from different indices in the array, even if the elements themselves are the same. The output for this problem is a single integer, representing the total number of good subsets modulo 10 to the power of 9 plus 7. To clarify this, let's look at an example. Suppose the input array is nums equals 1, 2, 3, 4. The output for this case is 6 because there are 6 valid good subsets. First, we have the subsets 2 and 3, which are good because each contains a single prime number. These subsets satisfy the condition that their product is divisible only by distinct primes. Similarly, there are other subsets that also qualify, which we will explore further. The key takeaway here is that for each subset, we need to verify that the product of its elements involves only distinct prime factors. Continuing with the same example, the remaining good subsets are 2, 3, 4, 2, 4, and 3, 4. Let's break this down. The subset 2, 3 is good because the product 6 is divisible by the distinct primes 2 and 3. The subset 4 is good because the product 4 is divisible by the distinct prime 2 repeated twice, but still satisfies the condition. Similarly, 2, 4, and 3, 4 qualify because their products, 8 and 12 respectively, involve only distinct prime factors. This gives us a total of 6 subsets for this example that meet the conditions. The explanation illustrates how subsets can combine elements while maintaining the distinct prime factor requirement. Now, let's consider a different example with nums equals 4, 2, 3, 15. In this case, the output is 8 because there are 8 good subsets. Specifically, these subsets are 2, 3, 15, 4, 2, 3, 2, 15, 3, 4, and 3, 15. For instance, the subset 15 is good because the product 15 is divisible by the distinct primes 3 and 5. Similarly, 3, 15 is good because the product 45 involves the distinct primes 3 and 5. This example highlights the importance of checking each subset's product to ensure it satisfies the distinct prime factor condition. Additionally, the inclusion of numbers like 15 demonstrates how larger numbers in the array can contribute to forming good subsets. Finally, it's important to address some constraints and edge cases. The constraints specify that the length of nums can go up to 10 to the power of 5, and each number in the array is between 1 and 30. This means our solution must be efficient enough to handle large inputs. For edge cases, consider when all elements in nums are 1. In this case, no good subset exists because 1 is not divisible by any prime number. Another edge case is when nums contains only one non-prime number, like 4. The subset 4 could still be good if it meets the distinct prime factor condition. These scenarios underline the importance of carefully handling inputs of varying sizes and compositions, ensuring our solution remains robust and efficient. To solve this problem, we first considered the brute force approach. The idea here is to generate all possible subsets of the given array nums, and for each subset, compute the product of its elements. Then, we verify if the product can be expressed as a combination of distinct prime numbers. This can be implemented using bit masking to generate subsets, followed by factorizing the product of each subset. However, the complexity of generating all subsets is 2 to the power of n, and the additional overhead of factorization makes this approach computationally expensive and impractical for larger inputs. Due to the exponential growth of subsets, this method quickly becomes infeasible, especially when dealing with arrays of significant size. To address this inefficiency, we turn to an optimized approach using dynamic programming. Instead of explicitly generating all subsets, we use a DP-based strategy to count subsets indirectly through their prime factorization. The key observation here is that numbers can be represented by their prime factorization as a bit mask, where each bit corresponds to a prime number. The steps involve pre-computing the prime factorizations for numbers up to 30, since the constraints limit the maximum value in nums to 30. Then, we create a frequency array to track occurrences of each number in nums. The DP table, DP mask, is used to store the count of subsets that correspond to the product encoded by mask. By iterating through each number in nums and updating the DP table accordingly, we effectively calculate the count of valid subsets without explicitly generating them. Finally, we sum up all valid subsets, excluding the empty subset, to get the result. This approach has a much more manageable complexity of n asterisk 2 to the power of m, where m is the number of primes less than or equal to 30. This dynamic programming approach offers clear advantages, as it efficiently handles the problem constraints and avoids the need to directly generate all subsets. An alternative approach using backtracking was also considered. In this method, subsets are built step by step, ensuring that the product remains valid at each step. This involves checking that adding a new number does not result in repeated primes within the product. While this approach is more efficient than brute force due to early pruning of invalid subsets, it is still slower than the DP method because of recursive overhead and the lack of memoization. Ultimately, the dynamic programming approach using prime masks was chosen as the most efficient strategy for this problem. This method leverages the small range of numbers, up to 30, and the limited set of primes to encode subsets succinctly. By focusing on prime masks and the frequency of numbers in nums, it avoids the combinatorial explosion of generating subsets explicitly. Key observations include the irrelevance of numbers greater than 30, the fact that valid products must involve distinct primes, and the ability to encode these combinations using bit masks. Additionally, the number 1 is treated separately since it does not contribute to the prime product but can multiply subsets. While the DP approach requires careful handling of bit masking and modular arithmetic to manage large counts, it strikes the optimal balance between efficiency and clarity. In contrast, backtracking and brute force methods, though simpler in concept, fail to scale effectively for larger inputs. This makes the DP approach the best choice for solving this problem within the given constraints. The problem asks us to find subsets of an array whose product can be expressed as a product of distinct prime numbers. To achieve this, the first step is to generate all the prime numbers up to the maximum value in the array. This is done using the sieve of Eratosthenes, which is an efficient algorithm for prime generation. By creating a Boolean array called is_prime and marking non-prime numbers as false, we can systematically identify all primes up to the largest number in the array. This is crucial because determining if a product is valid requires knowing the primes it can be factored into. Once we have our primes, the next step is to generate all possible subsets of the array. We can use bit masking for this, which is a powerful technique that represents each subset as a binary number. For an array of size n, there are 2n possible subsets, and each binary number from 0 to 2n, 1 corresponds to a unique subset. This systematic approach ensures that no subsets are missed and avoids the overhead of recursion, making it efficient for this task. After generating all subsets, the next step is to compute the product of each subset. If a subset is empty, its product is defined as 1. This step is important because the product determines whether a subset is valid. To verify this, we perform a prime factorization check on each subset product. Using the list of primes generated earlier, we identify the prime factors of the product and count their occurrences. If any prime factor appears more than once, the product is invalid because it violates the condition of distinct primes. On the other hand, if all prime factors are unique, the subset is valid. To keep track of valid subsets, we maintain a counter that increments each time a subset passes the factorization check. This systematic process ensures that we only count subsets whose products meet the problem's criteria. Several key insights help us understand the algorithm. First, the unique prime factorization property guarantees that every number can be broken down into a product of primes in one specific way. This makes it straightforward to verify whether a product is composed of distinct primes. Second, using bitmasking to generate subsets is particularly efficient for smaller arrays, as it eliminates the need for recursive subset generation. However, edge cases like subsets with a product of one or arrays containing repeated numbers require careful handling to avoid incorrect results. In terms of data structures, the Boolean array is_prime is essential for prime number generation, while the list of primes stores all primes up to the maximum value in the array. Finally, a simple counter variable is used to track the number of valid subsets, making the algorithm both modular and easy to follow. Analyzing the complexity, the sieve of Eratosthenes runs in O, n log n, where n is the maximum value in the array. Generating subsets using bitmasking takes O, 2 to the power of m, where m is the size of the array. For each subset, computing the product and performing prime factorization is O, k log p, where k is the number of subsets and p is the largest product. Together, this makes the brute force approach feasible for small arrays but computationally expensive for larger inputs. To optimize, we can use memoization to avoid recomputing prime factorizations for the same numbers. Additionally, the factorization process can be halted early if a repeated prime factor is detected, saving unnecessary work. Pre-computing the prime factorizations for all numbers up to the maximum value in the array is another optimization that can significantly reduce runtime. These enhancements aim to make the algorithm more practical for larger datasets while maintaining correctness. Here, we start by importing the counter class from the collections module, which will help us count the frequency of each number in the input list. Next, we define the class solution and the method number of good subsets, where the main logic will reside. We first define a list of prime numbers up to 30, as these are the only primes relevant to the problem constraints. Then, we introduce a helper function called calculate_mask. This function takes a number as input and calculates a bit mask representing the unique prime factors of the number. For each prime in our list, if the number is divisible by the prime, we check if it is divisible by the square of that prime. If it is, the number is invalid and we return a mask of 0. Otherwise, we update the bit mask to include the current prime. After defining this helper function, we use the counter class to count the occurrences of each number in the input list, storing the result in the variable frequency. Finally, we define the modulus value mod, which will be used to handle large numbers, and initialize a dynamic programming array, DP, where each index represents a possible bit mask. We set DP 0 to 1, representing the empty subset. Now we iterate over each number and its frequency in the frequency dictionary. If the number is 1, we skip it since subsets with just ones are handled separately later. For other numbers, we calculate their bit mask using the calculate_mask function. If the mask is 0, it means the number is invalid, so we skip it. Otherwise, we update the DP array, iterating from the back to the front to ensure we don't overwrite values we still need. For each previous bit mask, if it has no overlapping primes with the current number's mask, we update the DP value for the combined mask. This is done by adding the product of the current DP value and the count of the number, modulo mod. After processing all numbers, the result is calculated as the sum of all DP values, excluding DP 0, which represents the empty subset. Finally, we account for subsets formed by the number 1 by multiplying the result by 2 raised to the power of the frequency of 1, modulo mod. The method then returns the final result. Here, we start by defining the list of prime numbers that are less than or equal to 30, as primes will play a critical role in determining the validity of subsets. We also define a constant, mod, to handle modular arithmetic since results can grow very large. Next, we define a helper structure, prime masks, which maps numbers from 2 to 30 to a bit mask. This bit mask represents which of the primes divide the number. For each number in this range, we calculate its bit mask by iterating through the list of primes. If a number is divisible by a prime, that prime's corresponding bit is set in the mask. However, if the number is divisible by the square of any prime, it is deemed invalid for forming good subsets, and we skip it. Once processed, only valid numbers are stored in the prime masks map with their associated bit masks. After constructing the prime masks, we count the frequency of each number in the input array using a frequent array. This helps us avoid redundant calculations and efficiently handle duplicate numbers. Next, we initialize a dynamic programming array, DP, where DP, mask, keeps track of the number of subsets corresponding to a specific bit mask. Initially, DP, 0, is set to 1 to represent the empty subset. We then iterate through all numbers from 2 to 30. For each number, if its frequency is 0 or it's not in the prime masks map, we skip it. Otherwise, we retrieve its pre-computed bit mask and update the DP array. The update involves iterating through all previous masks in reverse order to ensure no overlapping primes between the current number's mask and the previous mask. If there's no overlap, we compute the new subset count by combining the current number's contribution with the previous subset combinations, applying modulo arithmetic to prevent overflow. Finally, we compute the result by summing all values in the DP array except for DP, 0, which represents the empty subset. This gives us the total count of valid subsets without including the number 1. To account for subsets containing the number 1, we use its frequency, as each occurrence of 1 can double the number of valid subsets. We multiply the result by 2 to the power of the frequency of 1, using modular exponentiation to handle large values. The method PowMod performs this efficient computation using the fast exponentiation technique. Once adjusted for the subsets formed by 1, the final result is returned. This implementation efficiently combines combinatorics, bit masking, and dynamic programming to solve the problem within the constraints. To solve the problem, we start by identifying the list of prime numbers up to 30, which are crucial for determining valid subsets. These primes are stored in the array primes. Next, we calculate the frequency of each number in the input array nums using a frequency counter. For the example nums equals 1, 2, 3, 4, the frequency count results in frequency equals 1, 1, 2, 1, 3, 1, 4, 1. We also initialize a dynamic programming array DP of size 2*10 because there are 10 primes, and each bit mask represents a combination of these primes. The first element, DP, 0, is set to 1 to represent the empty subset. The rest of the elements in DP are initialized to 0. Now, we process each number in nums to update the DP array. Starting with the number 1, it is skipped because it does not contribute to the product of primes. For the next number, 2, we calculate its prime bitmask using the calculate_mask function. Since 2 is divisible by the prime 2, the corresponding bit is set to 1, resulting in a bitmask of 0b1 or 1 in decimal. Now we update the DP array for the number 2. For the previous bitmask prev_mask equals 0, which corresponds to the empty subset, we calculate the new value for DP, 1, representing subsets where the prime 2 is included. Using the formula, dp, 1 equals dp, 1 plus dp, 0, asterisk frequency, 2, we get dp, 1 equals 0 plus 1 asterisk 1 equals 1. The dp array is updated to reflect this change and now looks like 1, 1, 0, 0. Next, we process the number 3. We calculate its bitmask using calculate_mask, 3. Since 3 is divisible by the prime 3, its bitmask is 0b10 or 2 in decimal. To update dp, we start with prev_mask equals 0 and calculate dp, 2 equals dp, 2 plus dp, 0, asterisk frequency, 3 equals 0 plus 1 asterisk 1 equals 1. Then, for prev_mask equals 1, we calculate dp, 3 equals dp, 3 plus dp, 1 asterisk frequency, 3 equals 0 plus 1 asterisk 1 equals 1. After these updates, the dp array becomes 1, 1, 1, 1, 0, 0. Next, we handle the number 4. Using calculate_mask, 4, we find that 4 is divisible by 2*2, which makes it invalid for subset calculations. Therefore, we skip this number. With all numbers in nums processed, we proceed to calculate the final result. The result is the sum of all dp values except dp, 0, which represents the empty subset. Using the formula, result equals dp1 plus dp2 plus dp3 % mod equals 1 plus 1 plus 1 % 10 caret 9 plus 7 equals 3. Since the number 1 appears once in the input, we account for its impact by multiplying the result by 2 caret frequency 1. This gives result equals result asterisk 2 to the power of 1% mod is equal to 3 by 2% 10 caret 9 plus 7 equals 6. The final result for this example is 6. Now, let's consider another example, nums equals 1, 1, 2, 3, 5. First, we calculate the frequency of each number, resulting in frequent equals 1, 2, 2, 1, 3, 1, 5, 1. The DP array is initialized again with 1024 elements, where DP, 0, equals 1 and the rest are 0. Starting with the number 1, it is skipped for now because it doesn't directly contribute to the prime product. For the number 2, we calculate its bitmask as 0b1 and update DP accordingly. For prev_mask equals 0, the calculation is dp 1 equals dp 1 plus dp 0 asterisk frequency 2 equals 0 plus 1 asterisk 1 equals 1. The dp array is updated to 1, 1, 0, 0. Moving on to the number 3, we calculate its bitmask as 0b10. For prev_mask equals 0, we update dp 2 equals dp 2 plus dp 0 asterisk frequency 3 equals 0 plus 1 asterisk 1 equals 1. For prev_mask equals 1, we calculate dp 3 equals dp 3 plus dp 1 asterisk frequency 3 equals 0 plus 1 asterisk 1 equals 1. After these updates, the dp array is 1, 1, 1, 1, 0, 0. The next number is 5. Its bitmask is calculated as 0b100. We then update the DP array by considering all previous masks. For prev_mask equals 0, we calculate dp 4 equals dp 4 plus dp 0 asterisk frequency 5 equals 0 plus 1 asterisk 1 equals 1. For prev_mask equals 1, we calculate dp 5 equals dp 5 plus dp 1 asterisk frequency 5 equals 0 plus 1 asterisk 1 equals 1. For prev_mask equals 2, we calculate dp 6 equals dp 6 plus dp 2 asterisk frequency 5 equals 0 plus 1 asterisk 1 equals 1. For prev_mask equals 3, we calculate dp 7 equals dp 7 plus dp 3 asterisk frequency 5 equals 0 plus 1 asterisk 1 equals 1. After processing 5, the DP array becomes 1, 1, 1, 1, 1, 1, 1, 1, 0, 0. To compute the result, we sum all DP values except DP 0, giving result equals sum DP 0 % mod equals 8 to 1 % 10 caret 9 plus 7 equals 7. Finally, since the number 1 appears twice in the input, we multiply the result by 2 caret frequency 1. Using the formula, result equals result asterisk 2 squared % mod is equal to 7 by 4 % 10 caret 9 plus 7 equals 28. This accounts for the subsets that include any combination of the 1s. The final result for this example is 28. The time complexity of the solution can be understood by breaking it down into key components. First, we have the frequency count, which involves using the counter operation to determine how often each number appears in the input array nums. This operation takes n time, where n is the size of the array. Next, we calculate a prime mask for each unique number in nums. This process examines a constant list of primes, 10 in total, and performs modulo operations for each prime. Since the number of primes is fixed, calculating the mask for one number takes 1. If there are k unique numbers in the array, the total cost for mask calculation becomes k. Finally, we have the dynamic programming update. Here, we iterate over all 2 to the power of 10 possible bitmask states for each unique number, as there are 10 primes. Each update takes 2 to the power of 10 for one number, giving a total cost of k asterisk 2 to the power of 10 for all k unique numbers. These components form the foundation of the solution's time complexity. Now, to complete the analysis, we consider the result calculation. This step involves summing all values in the DP array and making adjustments for subsets that include the number 1. Since the DP array has 2 to the power of 10 entries, this adds an additional 2 to the power of 10 overhead. When we combine all these operations, the total time complexity becomes n for the frequency count, k for mask calculation, k asterisk 2 to the power of 10 for the DP updates, and 2 to the power of 10 for the result calculation. As 2 to the power of 10 is a constant, the dominant term is k asterisk 2 to the power of 10. In the worst case, where all elements in nums are unique, k equals n, and the time complexity simplifies to n asterisk 2 to the power of 10. This ensures that the solution scales efficiently even for larger input sizes. Next, let's analyze the space complexity. The first component is the counter object, which stores the frequency of each unique number in nums. In the worst case, where all numbers are unique, the space required is k, with k being the number of unique elements. The second component is the dynamic programming array, which has a fixed size of 2 to the power of 10 to store values for each possible bitmask state. This requires 2 to the power of 10 space. Finally, there's the temporary variable mask, which is used during mask calculation and requires only 1 space. When we combine these, the total space complexity becomes k for the frequency counter, 2 to the power of 10 for the DP array, and 1 for the mask. This adds up to k plus 2 to the power of 10. In the worst case, where k equals n, the space complexity simplifies to n plus 2 to the power of 10, which is manageable given the constraints of the problem. To better appreciate the efficiency of the optimized approach, let's compare it with a brute force solution. A naive method would involve generating all possible subsets of nums and checking each subset to see if it satisfies the good subset condition. Since there are 2 to the power of n subsets, and checking each subset for prime factorization would take at least n operations, the brute force approach would have a time complexity of n asterisk 2 to the power of n. This is exponential and impractical for large values of n. In contrast, the optimized solution uses bit masking and dynamic programming to significantly reduce the complexity to n asterisk 2 to the power of 10. Here, the factor of 2 to the power of 10 arises because we are limited to 10 primes, making the solution linear in n but bounded by a constant factor. This optimization makes the approach feasible even for larger input sizes, highlighting its efficiency over the brute force method. Analyzing different cases gives us further insight into the solution's behavior. In the best case, if nums consist solely of the number 1, the DP update step is entirely skipped, leaving only the frequency calculation and result adjustment. This reduces the time complexity to n. In the worst case, all elements in nums are unique and require full DP updates for each number, leading to a time complexity of n asterisk 2 to the power of 10. The average case depends on the distribution of numbers in nums, but the time complexity remains bounded by n asterisk 2 to the power of 10. This case-based analysis confirms that while the complexity may vary slightly depending on the input, the solution consistently performs within the established bounds, ensuring reliable efficiency. Finally, let's mathematically confirm the big O complexity. The dominant term in the solution arises from the dynamic programming update. This step involves iterating over k unique numbers and updating 2 to the power of 10 bitmask states for each. As a result, the cost is k asterisk 2 to the power of 10. For large arrays, k approaches n, leading to a time complexity of n asterisk 2 to the power of 10. The space complexity is determined by the counter object and the DP array. Together, these require k and 2 to the power of 10 space, respectively, resulting in a total space complexity of n plus 2 to the power of 10. These calculations validate the efficiency of the solution and demonstrate its scalability, even for larger inputs. When working on this problem, there are a few common pitfalls to watch out for. The first is misidentifying valid subsets. A frequent mistake is including subsets where the product doesn't meet the requirement, such as failing to ensure the product is made up of distinct primes. This often leads to incorrect results or overcounting, so it's important to validate each subset carefully against the constraints. Another issue is inefficient subset generation. Generating all possible subsets without pruning unnecessary branches can result in exponential time complexity, which is impractical for larger inputs. Using techniques like backtracking can help optimize this process. Lastly, ignoring edge cases can cause major errors. For example, arrays containing zeros, ones, or very large numbers require special handling. Zeros can invalidate a product, large numbers can lead to overflow, and ones need to be managed to avoid skewing the count. Testing thoroughly against these edge cases is essential for a robust solution. Another common error is improper prime factorization. Some might assume that all numbers in the input are made up of distinct primes without actually verifying this. Skipping this validation can lead to incorrect outputs, so it's critical to properly factorize each number. Additionally, skipping pre-computation is a significant inefficiency. If you repeatedly compute prime factorizations during subset checks, it can drastically increase the runtime. Instead, pre-computing the prime factors for all elements at the start of the process can save a lot of time. Now, in interviews, understanding constraints is key. Pay attention to the size of the input. For example, if n is small, like 10, a brute force approach might be acceptable. However, if n is large, say up to 10 to the power of 5, you'll need optimized techniques. Backtracking with pruning is an excellent choice for subset generation, and pre-computing prime factorizations while using bit masks to track distinct primes can greatly enhance efficiency. When considering your approach, it's important to evaluate trade-offs. While brute force methods are simpler to implement, they aren't scalable for larger inputs. On the other hand, optimized solutions, such as those involving bit manipulation, require a deeper understanding but are better suited for handling large datasets. In an interview setting, it's also crucial to communicate your thought process clearly. Be sure to explain the trade-offs you've considered and justify the approach you chose. This shows not only your technical skills but also your ability to think critically. For further practice, there are several related problems worth exploring. For instance, LeetCode 90, which focuses on generating subsets with duplicate elements, or LeetCode 78, which covers basic subset generation. Other useful problems include LeetCode 46 on generating permutations and LeetCode 504 on base 7, which provides good practice with number representation and prime factorization. Now let's discuss some alternative approaches that can improve efficiency. Bitmasking is a powerful technique for generating subsets and tracking prime factors using bitwise operations. While it reduces computational overhead, it does require a solid understanding of bit manipulation. Another approach is dynamic programming, which involves maintaining a DP table to track achievable products with distinct primes. While this avoids redundant checks, it can increase space complexity, so you'll need to balance memory usage against speed. Finally, the sieve of Eratosthenes is an excellent choice for prime pre-computation. By using this method, you can efficiently generate all primes up to the maximum number in your input. While it adds some pre-processing time, it significantly speeds up subsequent factorization checks and is especially useful when working with larger datasets. Each of these methods has its trade-offs, so choose the one that best fits the constraints and requirements of your problem. Great job! To summarize, we tackled this problem using an efficient dynamic programming approach combined with prime factorization. Remember, key takeaways include mastering subset generation and understanding how to optimize for large inputs. Thanks for watching. Be sure to like, subscribe, and keep coding. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!